Good afternoon, everyone, and welcome back after lunch. I'm Shantanu Singh, and I'm doing my PhD research under the supervision of Professor George Weiss. And the topic of my presentation today is abstract nonlinear control systems. So let me give you an overview. Firstly, I'll give a brief introduction about infinite dimensional linear systems, specifically well-posed systems, which will bring us to the motivation of my research topic, followed by the objectives. And finally, I'll state the main results. And last but not the least, I'll discuss a bit about the future plans and the research directions. So let's get to it. So let's consider this nonlinear differential equation in finite dimensional space. So let's say Rn. And we know that if f is piecewise continuous in T and locally Lipschitz continuous in X, then this equation has a unique local solution. And if this Lipschitz continuity condition is satisfied globally on the entire Rn, then the solution exists globally. So for finite dimensional systems, it's rather easily verifiable, this Lipschitz continuity condition. However, when we move to infinite dimensional systems, things get a bit more complicated, even for the linear case. So let's look at this abstract Cauchy problem, x dot is equal to ax, where a is a possibly unbounded linear operator, and the initial state x naught belongs to the domain of a. And we know that if a is a generator of a strongly continuous semigroup, then this equation number 2 will have unique solutions, which is continuous and has values in the domain of A. So the natural question to ask is, what is a semigroup? And when will this operator A be a generator of a strongly continuous semigroup? So let's look at the first question. So a semigroup is basically a mapping from R plus to some Banach space X. And it satisfies these two functional equations. Well, just to give you a historical perspective, it was Cauchy in 1821 who first asked this question, which kind of functions would satisfy these functional equations. And of course, he answered the question, and the answer to it is the exponential function. Together with this functional equation, if this semigroup satisfies the strong continuity condition given by equation number 4, then we call it a strongly continuous semigroup. So now we come to the second question: what is the generator of a strongly continuous semigroup? So the generator is defined by these two equations 5 and 6. And we know that if A is a bounded operator, then the semigroup generated by it would be the exponential function given here. So this is all nice, but we want some nice conditions for A to be the generator of a strongly continuous semigroup. So the very important result was given by Healy and Yoshida in 1948. Where they said that if A is a linear operator, closed and densely defined, with a non-empty resolvent set, and if the resolvent operator satisfies this inequality number 7, then A is a generator of a strongly continuous contraction semigroup. And not too long after, in 1952, this result was extended to a more general strongly continuous semigroup and not just a contraction semigroup. So if, again, A is a linear, closed and densely defined operator, and it has a non-empty resolvent, then and the nth power of the resolvent operator satisfies this inequality number 8, then A is a generator of a strongly continuous semigroup given as T, and it satisfies, and the norm of this strongly continuous semigroup is less than or equal to m e to the power omega t. Then another very powerful result, and my personal favorite, is this Lax-Phillips theorem given in 1961, which talks about the generators of contraction semigroup. So if A is a densely defined and dissipative operator on certain Banach space X, where dissipative operator is defined as below, And the range of lambda I minus a for all lambda greater than 0 is the entire Banach space X, then A is a generator of a contraction semigroup. So for an abstract Cauchy problem, we sort of have all the pieces of the puzzles to talk about the solution of the Cauchy problem. However, in control theory, we are more concerned with the operators, which are systems which can be represented by equation number 9 and 10, where A, B, and C are unbounded operators, and D is a bounded operator. And we want to know when this equation number 9, this differential equation, will have some meaningful or well-posed solution. When I say well-posed solution, I mean that there exists a unique solution which continuously depends on the initial state and the input to the system. So, and if a system is well-posed, then we can represent it by this operator sigma tau, which is a family of bounded operators T, phi, psi, and F. And it contains the entire information of the system given by equation number 12 and 13. Just for the sake of clarity, P of tau is the operator of truncation here. So this brings us to the objective or the motivation of our research problem. So, let's look at this problem. So we have a wind tower, which is clamped at the bottom to the seabed. And it has a large rigid body with a huge mass on the top in form of nacelle and the rotor. And this tower, which is modeled as a Euler-Bernoulli beam, can have vibrations because of the wind striking against it or ocean waves striking against it. And the idea is to reduce the vibrations. So one clever way of reducing the vibrations in the tower is by installing a tuned mass damper in the nacelle of the wind turbine, where a tuned mass damper is basically a rigid body with a certain mass, and it is connected to the nacelle via a spring and a damper. So let's look at the differential equations or PDEs representing this coupled system of Euler-Bernoulli beam and the tuned mass damper. So over here, W is the transverse displacement of the beam, and psi is the horizontal displacement of the TMD on the floor of the nacelle. I'll not get in the details of this PDE. Rather, I'll give you a state space representation of this coupled system. And again, here A, B, and C are unbounded operators defined on the state space X. And input space U and output space Y, which is the space of complex numbers. So this we know that this by certain results given by Professor Ziaoui and Professor Wise, that this system is in fact well posed, and moreover, it is strongly stable. So this brings us the picture is nice, and we know the system is stable and it is well posed. However, we didn't model the effect of friction between the TMD and the floor of the nacelle. So let's look at the equation when we take into consideration the friction term. So as you can see, the friction term given here by the term in blue is F naught signum of the relative velocity. And now the equations become nonlinear and in fact set value. So this brings us to the objective. The first objective is to understand whether this nonlinear system with the set value damping term is well posed or not. And in fact, we answered this question, and the results have been published in IFAC World Congress 2020, where we proved that if n is a maximal monotone set valued operator, then in fact this system, the coupled system, is well posed, and moreover it is scattering passive. Now comes the second objective, is to extend this study to a more generalized class of systems, which can be represented by the differential inclusion 15 and the output equation 16. The inclusion term appears because obviously n is a set valued nonlinear operator. So for the rest of the presentation, I will talk about systems which can be represented by these two equations. And in order to get some to prove or to understand or to study this the well-posedness of this system, we would require a tool from the semigroup theory called the Lax-Phillips semigroup. So why we need this semigroup would be clear in a moment. So let's say we start with a well-posed linear system on the triple space X, Y, and U, where X, Y, and U are Hilbert spaces. And we define an operator given here by the Gothic T in equation number 17. Then this operator is strongly continuous semigroup on the triple space calligraphic Y, X, and calligraphic U, which are defined on the top of the slide. And this system, this Gothic T applied to Y naught, X naught, U naught contains the entire information of the system, basically from the past output, the present state, and the future inputs coming to the system. So what will and this semigroup has some nice properties, that if the initial system, the linear system, is scattering passive, that is, it satisfies the energy balance inequality number 18, then the Lax-Phillips semigroup generated by the system is contractive. And moreover, the norm of this semigroup is equal to 1 for all t greater than 0. So let's look at the generator of this Lax-Phillips semigroup. And it looks something like this. In equation number 9, this Gothic A is called the generator of this Lax-Phillips semigroup. So as you can see that we can in fact represent the entire system by a differential equation, an abstract differential equation as y prime, and this A, B operator applied to the x0 and u0 at 0 is basically x prime and u naught prime. So now it becomes clear that why we are using this tool, Lax-Phillips semigroup, because we can represent the entire system by one differential equation. But now we want to see what happens in the case of a nonlinear system. So let's say we start with a initial linear system which is well posed, and we add the nonlinearity as a perturbation to the system. And just to make it clear that this nonlinearity n is defined everywhere. So the domain of n is the entire state space X. So, okay, so now we can represent this. And now we have a nonlinear operator, but that's basically what we know at this point of time. We know about it. And one of the results of our work is that we have shown that in fact this nonlinear system represented earlier by equation number 15 and 16 can in fact be represented by this equation number 20, provided that n is a maximal monotone operator, maximal monotone possibly set valued as well. So, but at this stage we still don't know that whether it would generate a semigroup or what kind of semigroup. We have no idea about it. So let's look at what semigroups of nonlinear operators look like. So here we have a strongly continuous semigroup, and its generator is defined in the same way as it is defined for the linear semigroups. And then we have, there's not a lot we can talk about for or any kind of strongly continuous semigroups of nonlinear operators. But we do have a well-established theory about a subclass of these semigroups, which are the contractive semigroup, and which satisfy this equation given in the box. And if this contractive semigroup, if the semigroup is contractive, then the generator would be densely defined and dissipative. And moreover, this the generator will have a maximal dissipative extension, which could be possibly set value with the same domain as the generator. And if an initial value belongs to the domain of U, domain of this Gothic A, then Gothic A not Z0 is a unique element of smallest norm in the set A Z0. And the solution to the differential equation ZT would be represented by this Gothic T applied to the initial state. And it is, in fact, Lipschitz continuous and right differentiable for every t greater than 0. So now we sort of have some idea about how to approach the problem, provided that we know that this, provided that the semigroup is contractive. So we have some idea about its generator and the solution of the abstract differential equation, which was earlier shown to you. So now I can present my main results now that we have all the tools. So the main results goes like this. If starting from a scattering passive linear system, and as you remember, scattering passive implies that the system satisfies a certain energy balance equation, which was defined a bit earlier. So starting from a scattering passive linear system, if the nonlinearity is maximal monotone, possibly set valued, and it is defined on the entire state space X, then we can prove that X, the nonlinear system represented by equation number 23 and 24 is in fact well posed. And moreover, it is incrementally scattering passive. What I mean by incrementally scattering passive is basically this equation number 25, which inequality 25, where X01 and X02 are the two initial conditions, and U1 and U2 are two inputs. Then the solution X1 of tau and X2 of tau, the difference between this and the output would be less than or equal to the energy or at the initial time and the energy coming in through the input. So how do we do this? Basically, I just want to give you an idea how do we go on to prove this. So basically, let's say we can define operator A Gothic A by this equation number 26, and we add this nonlinear perturbation to it. Then and then further on, we split this operator into two operators, Gothic A and N tilde. We can say that A Gothic A is a maximal dissipative operator because it is derived from the initial scattering passive system. So as you remember, we start from a scattering passive linear system. And N tilde, which we have assumed to be a maximal monotone, N, which is a maximal monotone operator that we have assumed in the beginning. So minus of N would be maximal dissipative. And by using the theorem of Rockefeller the sum of two maximum mode operators, we can say that if the domain of Gothic A intersected with the interior of the domain of n tilde is non-empty, and in fact it is equal to the domain of Gothic A, then the combination of these two operators would in fact be maximally dissipative, and hence it would generate contractive nonlinear semigroup. And this is how we basically prove that the system is well posed and in fact scattering passive. There are certain technicalities which I have avoided just to keep it within the time frame. So we can discuss about this if somebody is interested. I can give more details about it later on. So that's basically what we have presented, and this result have been sent to Automatica recently. And in fact, earlier this week, we got some positive reviews. And we are hoping to resubmit it, and let's see what happens. So now let me just discuss a bit about my future plans or the future directions this research can go. So as you remember that we considered the nonlinear operator to be defined everywhere, which is required to use the theorem of Rockefeller. However, now we want to see whether if this operator is not everywhere defined and its domain is a subspace of the state space. So that is one problem that we are looking at right now. Then the second problem that we are looking at is to have a sort of a representation theorem for all kinds of nonlinear infinite dimensional system, which can be represented by equation number 15 and 16, which I showed you a few slides earlier. And finally, if there is still time left, because I'm hoping to finish the PhD by March or something around that time. But if there is still time left, then I would like to do like numerical analysis of the wind turbine and TMD coupled system, just to see how this friction term influences the stability, or how it affects in dampening out the vibration. And finally, of course, this is a far-fetched idea. I don't know if we'll have time for that, to do some kind of stability analysis on the nonlinear infinite dimensional system that we were referring to. So these are the list of publications. So the first one is from IFAC World Congress, where we talked about the wind tower coupled TMD system. And the second one is abstract nonlinear control system, which is basically what is the conference version of our paper, the paper that we have sent to Automatica. And it has been accepted in CDC, and the journal version is under review. Like I told you, we have some positive reviews, and we are hoping to send it out soon. So that's about it. Thank you. And by the way, I would like to take this opportunity to thank Nathaniel for our doubt clearing sessions related to functional analysis, and also Pietro for giving us this for all the discussions that we have in the lab as well. So that's about